Okay, structure of the elements. I think we got mostly through that. Plum pudding model. How we determine that there must be a nucleus, that the nucleus has the protons and the neutrons in it. It's very tiny and it has all of the positive charge and all of the mass. So these are the subatomic particles. We have electrons have a charge of -1. And we say a relative mass of 0, 1 over 1836 of the mass of protons and neutrons. Protons are positive. I like to show that little charge. And then neutrons are neutral. They have no charge, but they do have mass. So these guys have mass. They have mass and they live inside the nucleus. Electrons have essentially no mass and they're on the outside. All right, we have 4 fundamental forces. We have the force of gravity. That's pretty familiar. I think we talked about that a little bit. That says that 2 objects will accelerate towards each other on the basis of their mass. Totally wacky. It's actually quite strange. Okay, then we have the electromagnetic force, and that makes a little bit more sense. That has to do with positive charges and negative charges attracting each other or repelling each other, right? So this is on the basis of charges. Wait. All right, and then we have the strong nuclear force, which is very mysterious. I don't really understand it. This is this holds the protons in the nucleus. Because they're positive, they should repel each other. So how do they stay in there? I don't know. We just call it the strong force and it works. Okay, and then the weak force, what's the weak force? I don't think we talk about that too much. I think the weak force, so if you think about those electrons, right, these ones are the negative charges, and then this is full of positive charges. Why don't those electrons spiral into the nucleus? They would be attracted. Again, they don't. So we're going to give that a name. We're going to say that that behavior is represented by orbitals. The orbitals hold them in their space so that they can't go into the nucleus. So it's a little bit mysterious. Okay, so most of what we're going to do is going to focus on electromagnetic force. And that's the charge attraction or charges repelling. And that works really well on the scale of molecules. Not so much on the atoms, but on the molecules. So when we look at the nuclear forces, that's high energy physics. When we're looking at atoms and molecules, that's where the chemical domain. So we're going to be looking basically at the same charges repelling each other and opposite charges attracting each other. Now, if we add up the total number of protons and the total number of electrons, they'll add up to be 0, so that in that atom, it has no charge overall. So we're going to be working with neutral atoms first. All right, we talked a little bit about isotopes. Isotopes have different mass, and that has different mass because the number of neutrons can vary. So we're talking about individual atoms. So make sure that that's clear in your mind when we talk about carbon-12, carbon-13, or carbon-14. We're talking about an individual atom of carbon. And we can represent that one atom with our notation. So we have the mass number. That's the number of protons plus neutrons. That is a whole number, an integer value, no decimals. And we have the atomic number. That equals the number of protons. Now, if it's neutral, then the protons equals the electrons. And I wrote IFF, that's if and only if the atom is neutral, then the protons equals the electrons. Okay, so our first example, we're looking for sodium-23. Write the atomic notation. Do you remember the symbol for sodium? Na. And then this is giving us the mass number. The mass number can change. So that is the important part right there. And then what is the atomic number? Sodium. is over here, 11. All right, so this is the symbol, and then the protons plus the neutrons is that number, and the protons is that number. So if we take the difference, we'll get the number of neutrons, and that is what can vary. All right, let's do the same thing for magnesium, and then we'll do this table of isotopes. I've written some notes on there to make that distinction between the mass we see on the periodic table, looks like that, that has the average mass of all of the magnesium that has been sampled, that we sample. The natural abundance of isotopes. But in this question, they're asking about one individual, and that is a magnesium 26 atom. So we're never just going to use the decimal average. We're not going to round it. Okay, we'll talk a little bit more about that in a minute. Okay, how's that going? You got those neutrons? Are we ready to fill in the table? Now this is given in this notation, that's giving the mass number. Now maybe these are the main element, the main isotope, but maybe they're not. They're just an individual that exists. For all of these, the number of protons we can find easily on the periodic table. Carbon is number 6. Argon is number 18. And iron is number 20. Okay, so to get the number of neutrons, this is going to be, this one is A, and this one is P, right? So this is going to be A minus P. And how many electrons? If we're talking about neutral atoms, those will be the same. All right, so let's talk a little more about the mass. We actually, with these atomic mass units, we actually have a connection to reality. We can get a collection of atoms and weigh it in the lab. So it's not just some idea. There's actually a connection to reality and to data that we can measure. It's just a little bit difficult to measure a mass that is so small. So instead, we're going to measure a bunch of particles, a huge collection. So let's talk about what this definition is based on. I believe this definition was updated in either the late 90s or the early 2000s. Based on 1/12, oh, wrong one. 1/12 of a sample of pure carbon-12. So they removed any of those isotopes. It's just carbon-12. And what this does is it takes the difference between the mass of the proton and the mass of the neutron, and it splits it down the middle. So they're equal. They're off a little bit in the like 4th or 5th decimal places. So they're slightly different, but they're very close. But look on the periodic table, we get 12.01. So if you look on there, it's 12.01. And the reason we have this decimal place value is that there are some naturally occurring isotopes that have extra protons. So there's some isotopes that are a little heavier. In this case, we have carbon-13 is naturally occurring in a small amount. Now, of course, we're going to use a decimal percent, and I'm going to use this problem to take a look at the significant figure. So we have our decimal percent, and then this has a mass of 12. So those get multiplied, and I'm going to write that value here, and then I'm going to add them together, because when I add, I have to line up the decimal places to look at my significant figures. So most of the mass is going to come from that carbon-12. Then we've got a very small amount of the mass is going to come from the carbon-13. Line up your decimal places. And let's take a look at our significant figures. First, we have to do the multiplication. So this one has 5 significant figures. This one has 7 significant figures. So counting from the left, 1, 2, 3, 4, 5. In the second part, it's only got 4 significant figures because of the 1.108%. So 1, 2, 3, 4. That still has more decimal places than the top value, and that's because it's a small number. Okay, so I'm going to look at where I know those values, and my answer will be good to that place. So that matches the periodic table. We can use our general knowledge and understanding to figure out what must be. If we know how many isotopes there are, we can figure out which one must be the most prominent one. For example, this number is very close to 12. So most of the carbon, knowing there's 2 isotopes, carbon 12 and carbon 13, most of it must be carbon 12 because the average is very close to 12. So we're going to use that to determine the most abundant isotope for each of these. Now lithium is over here in group 1, and it has an average mass of 6.941. There's only 2 naturally occurring isotopes. Which one is the most predominant? Yeah, this one is much closer to 7, so that's going to be the main isotope. Do you see how that works? Let's do one for argon. Argon's average mass is 39.95. Which one is the most predominant isotope? Yeah, it's going to be closest to 40. Notice it's not always the heaviest one. With carbon, it was not the heaviest one. But in these examples, it just happened to be. Now, when we look at the periodic table, everything past element number 83, bismuth, everything past bismuth has its mass in parentheses. So polonium is 209. Those are all radioactive, which means that they decay to different elements. They break apart. And so this is the longest lasting isotope. So it's the easiest to measure. It's the one that's easiest to measure because it sticks around. For many of these ones, especially these guys made in the lab, they just exist for a very short time and then they decay. We also have some periodic trends. So we've been talking about how the atoms, like every time we move from element 1 to element 2, element 3, element 4, we add a proton inside the nucleus as we go across the boxes. We also add an electron in the outer shell, right? So we're adding protons in the nucleus, electrons in the outer shell. And so as they get bigger and bigger, more protons in the nucleus and more electrons in the shells, it makes sense that they get bigger. They're like the onions with more and more layers. So this trend in the downward direction, this one, makes a lot of sense because we're adding more and more stuff as we go down. All right, this trend, this one is a little bit harder to understand because we're really thinking about how many protons are in the nucleus. Let's talk about phosphorus. Phosphorus has 15 protons in the nucleus. And then I'm going to look at the electron number 15. And so in this area, right, I'm talking about 14 electrons in there, right? There's 14 electrons, and then I'm going to look at the outermost electron, the 15th electron that was added. And that experiences shielding from all of those other electrons. So how close it can get to the nucleus and how many electrons are blocking it from that positive charge all have to do with why it's held closer. Basically, these ones are smaller over here, and these ones are larger. Okay, so let me write that a little bit more clearly. I just wanted to talk about the issues at play there, right? So these are the largest elements, and these ones are the smallest. And you see the data right here. These values, I believe, are, yeah, I think these are in angstroms. So that I think is -10. Yeah, hydrogen's not listed there. That's the only one I know. Okay, so there's some trends. The other trend that goes in this same direction, remember our metals and nonmetals? So largest element, these are also the most metallic. And these are the nonmetals, right? So these are the least metallic. What does it mean to be more metallic? That's right. Shiny, conductive, malleable, all of those things. Those are the properties we're talking about. So we're going to compare those. We have our greater metallic character and we have our greater atomic mass. All right, sodium and cesium are straight up and down. So it's always a good idea to have one of these with you when you're working on chemistry. Handy to have it. So that one is a straight up and down trend. So clearly cesium is bigger. If we look at sodium is over here and aluminum is right here. Sodium is bigger. If we look at indium, it is right there. I don't know if you can see that. There's indium. And then iodine is on the end. So again, it's a cross. So indium will be bigger. Notice that if we had trends, I'm going to draw my little periodic table. The trend goes down to this bottom corner. So if I have a comparison that goes like that, right, it goes diagonally, then we don't know from the trend. Then we need data. If we have trends that go in this direction or across or down, then we can tell. But if it goes diagonally in the other direction, we can't tell. So these are all chosen to be able to determine using the trends. All right, so greater metallic character. So the metallic trends are going to follow the same trends. So these are going to have exactly the same answers because they follow the same trends. Okay, so next up, atomic masses. We calculated that average atomic mass for carbon. So let's take a look at that huge collection, right? If we had one atom, we'd have to weigh 10 to the minus 23rd grams. And we don't have any balances that are that accurate. We don't even have a way to get one atom conveniently on the balance. So when we measure, we're usually going to use a large collection. We're going to have so many. It's like weighing a bag of apples instead of just one apple, buying a 5-pound bag. So we use a counting number in chemistry, like a dozen. We have like a dozen donuts or a dozen bagels, or a pair of gloves. In chemistry, we use a mole. So this is our counting number in chemistry. It's a convenient number to measure of atoms because it represents a reasonable amount. Or it comes from the Latin word for a pile. It started with a pile of salt. Like if you put a kind of a large pile, maybe 2 tablespoons, I think, of salt, that's a mole of salt. It's something that it's a collection of atoms that is big enough we can measure it. And it's just a number, but it's a large number. So it works just the same way as a dozen. And when we write a factor, this is where it gets a little bit tricky. It's a little bit challenging because we have our number, we have our unit, and then on the other side, we just have a number, right? So normally we have a number, a unit, and a label. That's going to equal a number and just the label. So let me explain what I mean a little bit. I could say I have 1 mole of chairs. How many chairs would that be? That would be 6.022 times 10 to the 23rd chairs. So the label is the same. It could be anything. It could be eggs or donuts, what have you. It could be anything. So what we really have for our equivalence statement is 1 mole is that number. And then we have our label, right? So if I said 4 pairs of gloves, that means how many gloves? A pair equals 2, so that's 8 gloves. All right, so let's take a look at this. We'll do this with eggs. It's just like a dozen. So I'm going to show in dimensional analysis how many eggs equals 3 dozen. 1 dozen is 12. And that's where we get the label. We're going to get that label of eggs. We'll do exactly the same thing with moles now. 3 moles of eggs. I need to get rid of a mole of eggs, and I'm just going to go to eggs. So 1 mole, then the number goes on top. I'm not going to worry about significant figures right now because we're not going to count that many eggs. It's all theoretical in this. But somehow it gets harder when we start talking about carbon, right? When we start talking about the chemicals themselves. So focus on the moles. Don't focus on the atoms. If I write carbon, you know it's an atom. But if you write things like how many moles of atoms, then you wonder, is it moles or is it atoms? So moles is our counting number, right? That's like the packages, like how many dozens, how many reams of paper, how many pairs of gloves. So I'll just set this up for you and then we'll stop there and pick it up tomorrow. How many moles of carbon equals 1.25 times 10 to the 24 carbon atoms? Okay, so we'll stop there. Thank you.